All right, so this video is on how to sketch polynomials when they're written in the form where they have linear factorizations. So, and you'll see, actually I can just show you, if you look at the back, this is what a polynomial looks like when it's in its linear factorization form. So standard form is what you're used to seeing. That would be as if I wrote all these parentheses out like x minus 3, x minus 3, x plus 5, x plus 5, x plus 5, and I like FOILed it all out. Linear factorization form is kind of like we factored it, and then anytime we had a factor that repeated, we just wrote it with its exponent. So that's what we mean by that, essentially, is like the factored form. So first, what is the degree of a polynomial function? It is the highest exponent. So for example, if you had y equals x to the third plus 5x to the fourth minus x squared plus 2, you would say that the degree of this function was a degree of 4. If we flip the paper over and look at this problem, we have to think about what would have happened if we had FOILed it. So if I had this, I would have y is x times x minus 3 times x minus 3, x plus 5. This already looks terrible. X plus 5, x plus 5. So if we did that, eventually we would have had an x, 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 x. We would have had x to the 6th power as our highest exponent once we FOILed all of that stuff out. So we would say this one is a degree of 6. Now, we won't normally write all of that out because that's obnoxious. The way that we do it is we just count the exponent. So this would have an exponent of 1. 1 plus 2 plus 3 is 6. So this one would have a degree of 6. And again, I know that because if I was to FOIL out this whole problem, my highest exponent would have been 6. So either it's written in kind of like the standard form and I can just look for the highest exponent, or it's written in that linear factorization form and I have to count to get my degree. Okay, so next we're going to look and see what the degree tells you about the general shape of the graph. So if the degree is 1, it's just a linear graph, and we know that linear graphs look like this. If it's a quadratic, that's a degree of 2. We've seen those graphs before. We know that those just look like the U-shaped graph. Now, what you might not know is that if we do x to the 4th, the graph looks similar, it just grows faster, and so it's still a U-shaped graph, but it's just a skinnier U-shaped graph. And if I were to figure out what x to the 6th looked like, it would be the same shape, just skinnier because it would grow faster. And then if I did x to the 8th, it would do the same thing, it would just be skinnier. So whenever we are looking at something with an even exponent, when it has an even degree, we know that overall the graph is going to be kind of U-shaped. That was not symmetric at all. Okay, so when we draw a cubic, x to the 3rd, we've got something like this. They call that an S-curve. And then we can try x to the 5th, and you'll see that it grows faster, but it's still basically the same shape. So it's a little bit more narrow because it grows faster, it's more steep. And then if we check x to the 7th, we're going to see the same thing. So here, anytime we have a degree that is an odd exponent, that means that the general shape is going to be, it goes down and then something happens in the middle and it goes up, right? So next we're going to use these general shapes to describe the end behavior. So you guys have done this before. We know that when we write the end behavior, we should say as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. But we're going to kind of shorthand it for this because the end behavior, if you're using it as helping you do a problem, and in this case, it's going to help us draw our sketch. If the purpose of you writing that information down is to help you draw the sketch, then you don't need to be formal about it. You're just kind of taking notes. But if you're going to be formal about it, if I'm going to ask you the question, what is the end behavior, then you would have to write it out the way that we've written it out before. So what we're going to say is that if we have an odd degree, so this is an odd degree, a degree of 1 or a degree of 3, 5, 7, 9, anything, you can see that the left side is a down arrow and the right side is an up arrow. So if we have an odd degree and a positive coefficient, then the arrow goes down to the left and up to the right. Right? So that's like a positive x to the third, a positive x to the seventh. Now, if I take this and I put a negative in the front so I reflect it over the x-axis, then you can see that the arrows are going to go the opposite direction. So if I have an odd degree with a negative coefficient, then my arrow is going to go up to the left but down to the right. Okay, so those are the two ways that the overall graph can go if we have an odd degree. If we have an even degree and a positive coefficient, then we can see that the arrows go up. So the arrow is going to go up to the left and up to the right. So we'd say as x goes to negative infinity, y goes to infinity. As x goes to positive infinity, y goes to infinity. So both arrows would go up. If we have an even degree and a negative coefficient, that means if I put a negative in the very front of the equation, we would go down to the left and down to the right. Okay, so it's important to be able to count and figure out what the degree is and to be able to understand if the graph has a negative coefficient or a positive coefficient, because that will make a difference about where the arrows end up. And that's where we're going to start. All right, the next thing we're going to look at when we draw our sketches is we're going to find the multiplicity of the zeros or the x-intercepts or the roots. And so what I mean when I say the multiplicity, I'm wondering if that factor happens one time, if it happens 2 times, if it happens 3 times. We could say x plus 2 to the 7th if it happens 7 times. And that's the multiplicity of the root. It's how many times that answer happens. Okay. So roots, zeros, x-intercepts, they're all different ways of talking about the exact same thing. So if we have a multiplicity of 1, that means we might have an x-intercept of like x minus 4 to the first power. Okay, and whenever you have a multiplicity of 1, the curve is going to go straight through that number. So here is x equals 4, the curve would go straight through that. Okay, and actually I'm not going to put arrows because this is going to be not the entire graph, it's just going to be the middle of the graph. Or we could say maybe we have x plus 5 and it went through this way, but to fit the curve it had to go negative. So we have 2 options with a multiplicity of 1. You can go straight through slanting to the right or straight through slanting down to the right. So either or. A multiplicity of 2 or 4 or 6 or 8 would be like x plus 3 to the second power or x squared. That's what they would look like. And we have 2 options here. It could be a parabola that's coming up underneath the x-axis, or it could be a parabola that's coming from above. And so what a lot of people say is they say this one is straight through, and they say that a multiplicity of 2 or a multiplicity of 4, we could say x minus 7 to the 4th here, that these bounce. They bounce off the x-axis, they don't go through, right? Multiplicity of 3 could be like x plus 1 to the third power, or x minus 4 to the third power, or x to the fifth power, something like that. These ones go through, but they don't go straight through, they squiggle through. So it goes up, levels out, continues to go up, or it could go down, level out, continue to go down. So what you'll notice is that at each individual x-intercept, you see the same sort of shapes as what's happening with the overall graph, okay? So this is kind of like big picture perspective. This is like if you were to zoom out, this is what you would see. This is kind of like if you zoom in and you want to see what's happening at each individual piece, okay? So now we're going to combine those ideas and we're going to look at these. We're going to do some of these examples in the video and then some of the examples we'll do in class. So this is a degree of 6. This equation has a positive coefficient because there's no negative in front of the equation. So I'm going to say this is a positive coefficient. And so that means since it's even and positive that the arrows go up and up. All right, so I know on the left side of my graph, my arrow is going to go up. On the right side of my graph, my arrow is going to go up. And so I just put these to start with so that I know where my graph needs to end. What I do next is I figure out each of my x-intercepts. So I have an x-intercept of 0 and 3 and -5. And I figure out what the multiplicity is for each one of those. So multiplicity of 1, multiplicity of 2, multiplicity of 3. And then what I do is I draw those x-intercepts on my paper. So I have an x-intercept of 0, an x-intercept of 3, and -5. And then what I do is I start on the left side of the graph and I work from left to right. So if we look at this, on the very left, that's -5. That has a multiplicity of 3. And so that is the option that needs to squiggle as it goes through the graph. So we have two ways it can go. It can go like this, which if you look at this and know that you have to connect your arrow this way doesn't make a lot of sense. Or it can go like this. And that way makes a lot more sense if this arrow is what we have to go through. So what I'm going to do is I'm going to draw the arrow, and then I'm showing that it squiggles as it goes through that point. Okay. Next, we have 0 right here. So we know that with a multiplicity of 1, it can go straight through like this, or it can go straight through like this. So if we look at what we have here, it makes a little bit more sense for it to go straight through here because then it can connect easily to the green that we've already done. So I'm going to go ahead and underline this because that's one we just did. So now with this color, I'm going to show that this is what we're doing here. And then I just need to make sure that my two pieces of the curve connect. And the pieces should always connect with a smooth curve. So I'm going to make this look smooth. Okay, so it shouldn't be like a sharp corner. It should go kind of smoothly through that. And then the last one I have is that parabola. That's the U shape. So I have two options. I can have a U shape from above, or I can have a U shape from below, like that. And I have to connect through this arrow, so it doesn't make sense to do the U shape below. I'm going to have to do it from above. I'll go ahead and say U shape from above, connect to that arrow, and then I just need to connect these two and make a smooth curve. And so that's about what that graph would look like. So overall, since this is a degree of 6, if I was to like zoom out of this picture, it would basically be a U-shaped graph. It's got like a little bit of weirdness in the middle, but it's U-shape. And then if I zoom in, which is what I've done here, then I can look and see that at this x-intercept it goes straight through because it's a multiplicity of 1. At this x-intercept it squiggles through, and at this x-intercept it kind of bounces. Okay, we'll go ahead and do one more, and then we can leave the other ones for in class. So this one has a degree of 3. We have 2 there and a 1 right there. It has a negative coefficient. So negative coefficients go up first and then they go down, right? Because up first and then going down means you are slanting down. So that's a negative slant. We have 2 x-intercepts, one at 0 and 1 at -5. And we know that the arrow goes up and then it goes down. So if we look at -5, that one has a multiplicity of 1. So we know that we have two options. We can go straight through like this, or we can go straight through like this. And this is the option that makes more sense if you have to connect to that arrow. So I'm going to say arrow and then straight through. And then for the other one, we have the x-intercept of 0, and that one has a multiplicity of 2. And so we have two options there. We can have the U-shape from above, or we can have the U-shape from below. And if we look at how it connects to the arrow, it makes a lot more sense for that U-shape to come from below. So now I just need to connect the curves so that it's a smooth curve. So overall, this has that kind of S shape where it comes down like this. If we were to zoom out, that's basically what we would see. But zoomed in, we can see that straight through, and we can see that bounce right there. All right, so that's all you should have done on your notes. Do not do the rest of them. We will do those in class together.